Hi, in this video, let's discuss continuous functions. Let's begin with a definition. A function f is said to be continuous at x equals a is a number, if the two-sided limit of f of x as x approaches a is exactly equal to f of a. So from the definition, there are several things to notice. When we talk about concept of continuity, it is always continuous at some point. That's the phrase to look for. And also to check for continuity at a point, we need to look and see if this equality holds true. From here, it's clear for a function to be continuous at x equals a, f of a must be defined, and the left-hand limit, the right-hand limit must exist, and they must both equal to this f of a. It's nice to understand continuous functions by looking at functions that are not continuous. Here are graphs of functions that are not continuous at x equals a, and we will examine each one and see why they fail to be continuous. Most likely because maybe f of a wasn't defined, or f of a was defined but maybe one of the limits, left hand or right hand, did not exist, or they existed but they weren't equal, or they were both equal but they were not equal to f of a. There are many ways that a function can fail to be continuous at a point. So let's look at this example. Here right away you can see f of a is not defined. That itself tells us the function not continuous, and we could move on to another graph, but also pause and look and see the left-hand limit is also not equal to right-hand limit. So there are many reasons why this function is not continuous. Here f of a is defined, but the left-hand limit and the right-hand limit, they exist but they're not equal. So this function is not continuous. Here f of a is not defined. That's enough reason to say this function is not continuous at a. Also notice the left-hand limit and the right-hand limit do not exist. So that's another reason why this function is not continuous. Let's look at this one. This is also a function that's not continuous. The reason being f of a is not defined. That's what that open circle is telling us. That's not a point on the graph. Here notice that the left-hand limit and the right-hand limit exist and they're equal to L. So the two-sided limit exists. This function would be continuous if the two-sided limit, which is L, was exactly equal to f of a. But in this one, f of a is not defined. If we could just define f of a to be L, that is, if we could just patch up that hole with a dot, then this function would be continuous. And you're correct. So this kind of discontinuity is sometimes called removable discontinuity, because you can define f of a as L and make this function continuous. Now let's look at a few more exotic examples of discontinuous functions. Here's the function f of x equals sine 1 over x, and remember x is in radians. You've seen this function before. Use technology to draw the graph, and if you like, zoom at x equals 0, and you will see that in any interval surrounding 0, you will see the infinite number of these oscillations. The oscillations are always between -1 and 1 and so on. And today we claim that this function is not continuous at x equals 0. Firstly, notice that the function is not defined at x equals 0. Furthermore, you can convince yourself using a table of values or by zooming in on the graph of this function. When you graph it using some technology, you'll see that the left-hand limit and the right-hand limit do not exist because of what is said about the oscillations, infinite number of oscillations in any interval around 0. So in this case, even if you tell yourself f of 0 is not defined, maybe I can define it myself. I cannot put 0 into this function. Maybe I can just declare f of 0 is 0, or f of 0 is half, or no matter what number you choose, there's no way you can make this function continuous at x equals 0. The real reason why this function fails to be continuous at x equals 0 is because the left-hand limit doesn't exist, the right-hand limit doesn't exist, and we can't fix that. So keep this example in mind together with this picture and all the facts about this example. If you want some neat vocabulary, you can think of this as an oscillating function with a discontinuity at x equals 0. Now let's look at another example. So we just finished discussing this function, which we said is not continuous at x equals 0, since the one-sided limits did not exist for that. So let's look at this function, which is only slightly different from this function. Notice that I put in an x. Convince yourself that for this situation, the two-sided limit does exist and it's equal to 0. You may use technology to draw this kind of a graph, which is also an oscillating function, but it oscillates in this manner, and maybe perhaps by zooming in, once you graph this on technology, you'll be able to convince yourself that the two-sided limit is 0. Again, we are keeping our discussion at an intuitive level. You could also create a table of values to convince yourself that the two-sided limit exists and is equal to 0. One thing to notice is, once again, f of 0 is not defined. We could not put in 0 because of this 1 over 0, and division by 0 is undefined. And so f of 0 is not defined, and it's for that reason f is not continuous at x equals 0. Notice, because the two-sided limits exist and they're equal to 0, there is a way to patch up that hole at that point x equals 0. If you could only define f of 0 also as 0, then this function would be nice and continuous at x equals 0. That's exactly what this example is saying. Here we have a piecewise function, g of x. When x is not equal to 0, we define it exactly as this, x sine of 1 over x. So its graph is exactly same as this. But when x is actually 0, then we say g of 0 is 0. We are defining it by hand. We're not using this formula. So in fact here, by defining it this way, we're simply patching up that hole. And so the graph of this is exactly this, and also that hole patched up. And so here, for this function, we can make this sort of a conclusion. The two-sided limit exists. It's equal to g of 0, because we've defined g of 0 as 0 equals 0. So because of this, we can conclude that g is continuous at x equals 0. So keep these important examples in mind and look at them together so you can compare and contrast them. Continuous functions are very nice to work with. Remember that if f is continuous at x equals a, by definition, that means that the two-sided limit is exactly equal to the functional value at that point. So if we are asked to find a two-sided limit, up until now our only tools were creating a table of values and estimating the limit, or looking at a graph and estimating what the two-sided limit would be. If you're given a continuous function, that means what this one is implying is the two-sided limit is exactly equal to f of a. Clearly, f of a is easy to compute. If you're given a formula for f, all you need to do is put in a as an input for x and get a number. That would make it very easy. In fact, that's the approach we're going to be taking whenever we ask to find two-sided limits of functions that are continuous. Next, we will prove many important theorems about continuous functions, and then we'll see how we can apply it to problems. Thank you.